Good morning, folks. My name is Craig Harrigy. I'll be your instructor for conceptual physics this semester. I wanted to make this video today, first of all, just to kind of introduce you guys to the class, but also because there's just a few things I want to discuss at the beginning. So just a little bit of information about me. I've been teaching since 2001, I believe was the first class that I taught. I have a bachelor's and a master's degree in physics from Mississippi State University and a PhD in education, or essentially educational statistics, from the University of Southern Mississippi in 2019. I am from Mississippi, so I am actually an hour behind you guys, as you guys are on Eastern time, I believe. If you need to contact me, if or when you need to contact me, you can use this email address here, or you can text this number if you need. Please don't just cold call me. I won't really answer it. My phone doesn't really ring all that well. But you can contact me any way that's convenient for you. Reach out to me anytime. You're not going to bother me. It just might take me a minute to get back to you sometimes. So feel free anytime that you need to reach out to me. Now, the reason that I'm making this video today, and that if you somehow started looking at the videos 2 hours ago, right as the class opened up, you won't have seen this, is because some of my lecture videos that you guys will see discuss concepts that I discussed in other classes. I've been teaching for a long time. And so there are some things there that I don't feel like I need to reinvent the wheel, I guess. And so they may look a little different, but all the information is there. And I'm also going to share some videos with you from people who aren't me, and other things that I can't really show you each week. Try not to let all the different section numbers and things confuse you. The information is what's important, so just kind of focus on that. I'll make some other lecture videos like this one to show you some example problems, right? And to just kind of talk through some things with you each week if I feel like it's necessary. There may or may not be a video like this each week, depending on what you guys are doing. I would assume you'll get at least a brief video with some examples each week, or almost every week. In that case, make sure that you watch all the videos that I post. They're all going to be helpful to you, and you should be able to learn something from everything. They're not excessively long, and so it should be kind of easy to go back and forth and refresh your ideas in your head. This video is going to talk about some of the examples that you will see in your Connect assignments this week. So in that Smart Book assignment and in the practice questions, particularly the practice questions. So I'm going to briefly talk about some ideas, but there's also, these ideas are also covered in those other videos along with the other concepts. So I am making that part of it brief so that we can talk about the example problems. So remember that we first talked about average speed this week, or that's one of the things that we're going to talk about this week. Okay, and the average speed of an object is just the distance that the object travels divided by the time that it takes for it to travel that distance. And we can use this equation here to solve for the time or the distance if we know the speed of some moving object. Okay, and so 3 different formulations of the same equation. So let's look at an example. You're at a football game and you're watching the opposing team's marching band warm up from the other side of the stadium, right? You notice that you can see a drummer strike his drum 1.3 seconds before you can hear it. Now I add this example because this is true. If you're standing on the other side of a football stadium and you watch the opposing band's drums, right, you'll notice that you can see them hit the drum before you'll hear it. Okay, that's because sound has a definite measurable velocity that we can all observe, and so it takes time for the sound to travel across the field, right? So given that sound travels at 1,087 feet per second, right? So that's our speed. How far away is the drummer, right? Well, so we're looking for the distance, and so remember that the distance is equal to the speed times time. And so that would just be 1,087 feet per second times 1.3, and I'm just going to throw this 1.3 seconds. I'm just going to throw this in my trusty calculator real quick. 1087 times 1.3, 13.1 feet. If we divide that by 3 to convert it to yards, and I just did this because I made this example up, that's 471 yards. That's a pretty big football field. But that's what happens when you just kind of throw some numbers in an example. Regardless, in order to find the distance, right, you just want to multiply the speed times the time. Now, you know this in a way based on calculating things like when you're driving, trying to figure out how far you're going or how long it's going to take you to get somewhere. And a lot of the time, I guess Google does that for you now more than you might do it yourself. But the ideas are all still the same, right? So let's look at another example. Remember that the average speed is the distance that an object travels divided by the time that it takes, however long it takes for it to travel that amount of time. So we have a man who runs for 3 kilometers at 12 kilometers per hour, okay? And then he slows down and runs at 5 kilometers per hour for 30 minutes, right? So what's the average speed of the run? Well, what we need is the distance and the time of both motions, if you will. However, we only have one of each, right? And neither one is the same. So we kind of have to put them together and figure out one from the other. Okay, so we know that speed is equal to distance over time. And I'm just going to write this like this so that I can keep track of everything. Okay, and we're going to use this equation a couple of times. First, we know that the man runs for 3 kilometers at 12 kilometers per hour. Okay, and we want to calculate, we're going to need the time that he travels there because we know the speed and the distance. Okay, and so the time, if you will remember from before, is the distance divided by the speed. And so that gives us, let's see, 3 kilometers divided by 12 kilometers per hour. Okay, and we're going to get 1/4 hours, right, or 0.25 hours. Okay, and recognize, you guys, 1/4 of an hour, 0.25 hours, right, is 15 minutes. That messes people up a lot. Now, he slows down, and he's going to run at 5 kilometers per hour for 30 minutes. So now we need to know the distance, right? How far did he go in that 30 minutes? Well, in that 30 minutes, he went 5 kilometers per hour. Sorry about the units there. Let me fix that. As you will see in future problems, units are very important in physics. 5 kilometers per hour for 30 minutes. Well, 30 minutes is 0.5 hours. We want to make sure we have the same units here, hours and hours. And if we multiply 5 times 0.5, I don't need a calculator for that. That's 2.5 kilometers. So the average speed, let me change colors real quick. The average speed is going to be the total distance, right? So 3 kilometers for the first part, 2.5 for the second part. So 3 plus 2.5, or 5.5, divided by the total time, right? The first part of the trip was 0.25 hours. The second part of the trip was 0.5 hours, or 0.75 hours, okay? Or in this case, 45 minutes, if you will. So notice the distance is in kilometers, time is in hours, and our average speed, 5.5 divided by 0.75, 7.33 kilometers per hour. Notice that it's somewhere in between the two speeds that he was actually traveling. And that's what you would expect to find. The goal here is just to find the distance for the whole trip and the time for the whole trip to find the average speed. Distance is very different from what's known as displacement. When you want to find what's called the displacement of a moving object, all that matters in this case is the difference in position between the object when it starts moving and the object when it finishes moving. Right? The final position minus the initial position. Okay? You will often see it written as x final minus x initial. It's just telling you the difference in position is the displacement. Why does that matter? How is that different from distance, right? So assume you guys walk 1,000 feet from your car to your class, and then you walk 1,000 feet back to your car. Right? The total distance that you travel is 2,000 feet. Okay, but because you ended in the same place that you started, your displacement is 0. Displacement is important because it's how we measure velocity. Okay? Displacement is a vector. Okay? Recall that vectors have magnitude and direction. Okay? And so it's not just the amount, but it's which way. And so when we talk about a vector, we need to have a direction associated with it. If there's not a direction associated with it, it's not a vector. Okay? Distance would be a scalar quantity. There's no direction associated with that, 2,000 feet. But displacement is a vector, and it points in the same direction, or it points in the direction that the object travels from initial position to final position. And that's the direction. If for some reason you have a motion in 2 dimensions, which I'm going to show you this, right? So something moves to the right and then it moves up, right? In order to find the displacement, the difference between the initial and final position, initial and final position, you need to use the Pythagorean theorem, right? A squared plus b squared equals c squared. When it comes to vectors, the Pythagorean theorem is really, really important. Okay, so review it if you're unfamiliar with it. Ask me questions. Anything that you guys need, I'm more than willing to help. I've got tons of algebra videos and things like that if you guys feel like might be helpful, I'll be more than happy to share them with you. But let's talk about an example. A rock climber has starts at his car, and then he travels 300 meters to the face of a cliff, and then he climbs 500 meters to the top of the cliff. What's the rock climber's displacement? Right, and so you'll see why very quickly. I'm a physicist and not an artist. We're going to draw a car. That's actually not so bad. That's one of the better ones I've done. This is the guy at his car. Okay, so he's going to start here. This is his initial position. We'll call it X initial, just because. He is going to travel 300 meters to this giant cliff. And then he is going to climb up the cliff until he gets to the top. So what is his displacement? What is the difference between his initial position and his final position? To do that, we would use the Pythagorean theorem. Sorry, I left the number off here. And so this is C. And so C squared is equal to A squared plus B squared. Doesn't matter which one's A and B, but we'll call this 300 squared plus 500 squared. So you're like 90,000. Yeah. plus 250,000. And then when you add those two together, 340,000. And then we'll take the square root to get C. So we take the square root of both sides. The square root of 340,000, 583, call it 0.1, 583.10. So even though he traveled a distance of 800 meters, right, the displacement from his original position is only about 600 meters. And so that's the difference between distance and displacement. If we want to find the velocity of an object, velocity and speed are often kind of mixed up and interchanged. Okay, but the velocity of an object is different from the speed of an object in the same way that distance and displacement are different. And the velocity of an object is just the displacement of the object over time. And we'll sometimes write this as x final minus x initial. Okay, delta in front of a variable like t, this implies a change, right? So the change in time. So the final time minus the initial time. When we write time in these equations, we often just assume the initial time is 0. And so we'll often just write this as t. Either way is fine. This should look kind of like a slope formula from algebra, if you're familiar with it, because it's similar to that. Okay, just like the displacement is a vector, velocity is a vector, and they point in the same direction. Now, acceleration, right, refers to a change in speed. More appropriately, it's a change in velocity, okay, or a change in the direction of the object. If an object experiences uniform acceleration, okay, this means constant acceleration, the same amount of acceleration. Become familiar with this, because when you drop something, everything accelerates at the same rate. There's uniform acceleration due to gravity. At first, we're going to talk about it. Eventually, you're going to measure it. Now, if something has uniform acceleration, it will either speed up or slow down, or it will constantly change directions. Okay, an object can travel at the same speed and still have an acceleration if it's moving in a circle, because the direction is always changing. If an object, and here goes a really terrible drawing here, but if an object is moving in a circle around the circle, right, its direction is constantly changing. So even if the speed is the same, it can still have an acceleration. So we'll talk about that more in later chapters and discussions. But for now, acceleration is what you think of when you hit the gas pedal in your car, your speed up, right? Your accelerator. And so let's just talk about a couple of examples with acceleration. Okay, so a race car can accelerate from rest to 75 miles per hour in 4.5 seconds. Right? If the race car can maintain that same acceleration, that uniform acceleration, how long would it take to reach 200 miles per hour if the car starts from rest? Now we know there's a couple of ways to think about this, and I'm going to show you guys probably the easiest way overall. But we know that the acceleration is the change in velocity or the change in speed, right, over time. Rest just means it's not moving. So its initial speed is 0. and its final speed is 75 miles per hour. So the change in this case, 75 miles per hour in 4.5 seconds. Now we know if the acceleration is the same, that would have to be equal to the same acceleration when it accelerates to 200 miles per hour. But the thing we don't know here is the time. If the acceleration's the same, all we need here is this amount of time. And so to calculate that, just like you would any other algebra thing, you'll just cross multiply with this proportion. Proportions can be helpful in some cases, but I'm going to show you in a different way in just a second. So 75t is equal to 200 times 4.5 is equal to 900. If we divide by 75, and once again, you guys, if you need some algebra reviews, please just ask. I will be glad to help you with anything like that. It'll take you 12 seconds to get to 200 miles per hour. If it takes 4.5 seconds to get to 75. But there's another way that we can think about this. And this is one of the more important components of physics in general. In physics, we have what are called kinematic equations. Okay, and these kinematic equations, there are 3 or 4 of them, depending on what textbook you have, and they all kind of look a little different depending on what symbols you use, but they're all still the same thing. They're used to describe the motion of objects that have a constant acceleration. One of the simplest ones for me to show you comes directly from the idea of acceleration, right? Change in velocity over time, right? Again, that delta just means the final minus the initial value. And here we're just going to write delta t as just t again. If we do that and just do a little bit of algebra, okay, and so I can kind of show you the algebra. It's not much algebra. And it's very similar to what we did just a minute ago. The change in velocity has to be equal to, okay, the acceleration over 1. Okay, but we're really just going to cross multiply. And what you wind up with is the change in velocity is equal to the acceleration times the time. Okay, and this is probably the more common formulation of the equation, right, where the final velocity of an object is equal to the initial velocity plus its acceleration times time. This only works when something is accelerating at a constant rate. Okay, but everything that falls from the air accelerates at a constant rate. And so this becomes really helpful very quickly. There are other kinematic equations, okay, that are derived from, I think, this equation and different ways of writing certain things. But for now, I just wanted to show you guys this one because it's really useful in problems that you might see. And if you know that the acceleration is constant, you can always use these equations. So finally, in the last example, we have the brakes of a car cause it to slow down with an acceleration of -10 feet per second squared. Okay, so acceleration is equal to -10 feet per second squared. If the car stops in 4 seconds, so the time is 4 seconds. Okay, so you're driving in your car, you slam on your brakes, your car stops in 4 seconds. You know how your car slows down when you hit the brakes, right? You know the acceleration. And what was the speed of the car before the brakes were applied? Well, we can use that really simple formulation of the kinematic equation. And I'm actually going to use the first version of it so I can save you all a little bit of algebra. The change in velocity is equal to the acceleration times time. We know that the car stops in 4 seconds. Stops means its final velocity is 0. And that's the only thing that we're not directly told here. If it stops moving, we want to know how fast it was moving when it started moving. What was the speed before the brakes were applied? And so, to calculate that, we just need to plug in our acceleration and time. Negative 10 feet per second times 4 seconds. And notice these negative signs will cancel out. And the initial velocity was 40 feet per second. And we can divide by -1, if you will. You would expect that if something is slowing down, the change in velocity is negative. If something is speeding up, the change in velocity is positive. And so I think these examples should help you with some of your Connect assignments. Hopefully, the other videos will help you with some of the concepts. Make sure that you're reading through the textbook as well and doing those smart book assignments. All of these things will help as you're going through and learning about physics. I'm going to share as much as I can with you and as much good information as I can share with you. And hopefully you'll be able to use that. And if you have questions or if anything comes up, please email me or text me at the number that's here, and I'll be glad to help as much as I can. And next Friday, I'll post some more lecture videos and some more assignments and things for you all to do. If you have any trouble, please contact me this week. Have a great week, you guys. I'm going to stop for today.